Hello, everyone, and welcome to this webinar, a joint production of QuEra and Ghalbouni Consulting. Today, Joe Ghalbouni, president of Ghalbouni Consulting, is here. Joe, how are you today?
I'm doing fine, Yuval. How about you?
I am doing great, living the dream. And my name is Yuval Boger. I'm Chief Commercial Officer of QuEra. Today, we're going to talk about quantum computing for financial services. We're going to talk about the strategic risk as well as the emerging opportunity. You know, when people talk about quantum and qubits, they say, oh, it's like a coin spinning that is, you don't know if it's going to be heads or tails. Of course, don't say it has both positions simultaneously. That's not accurate. But the reason I bring it up is that when financial services companies are looking at quantum computing, they do see both sides of the coin. On one hand, they see tremendous opportunity to leverage quantum computing to solve problems that are difficult or expensive, to solve classically or just get better solutions. And on the other hand, the other side of the coin, they see the risk. So we want to talk about that. And the audience, of course, is first, thank you very much for being here, but also feel free to submit your questions on the Q&A box at any time, and we'll do our best to address them. Just a little bit about QuEra. I'll just chat a few minutes about that and then hand it over to Joe, and then I'll come back. You're not going to get rid of me that quickly. QuEra is headquartered in Boston. By now, we have offices in the UK and Tokyo, and recently announced that we're opening an office in New Mexico. We are born out of collaboration with Harvard and MIT. 4 of our founders are 2 professors at Harvard and 2 professors from MIT. And that relationship with Harvard and MIT is really one of our secret weapons in terms of being able to continuously collaborate in ideas, in science, in people, and equipment, and so on. We believe, and I think a lot of people believe that we're both the scientific and commercial leader in neutral atoms, and that neutral atoms are perhaps the most promising way to get to where we all want to go, large-scale fault-tolerant quantum computers. Our computers are available. Our first computer has been available on Amazon Bracket since November of 22. 3.5 years ago. It's still going strong, 130 hours a week. It's sort of the system that refuses to die, not because we can keep it running, we can keep it running, but because users continue to want to use it and get some amazing scientific results. And then we have a gate-based machine that's installed in Japan at the AIST, the National Institute of Standards. That's the one you see in this picture here. And then we have other machines in other parts of the world in various stages of development and build. We're well funded. Last year, we raised, give or take, $250 million, primarily from Google and SoftBank. NVIDIA also participated. And our success is being recognized in multiple ways. One of them is that we were selected for stage A and now for stage B of DARPA QBI. QBI Quantum Benchmarking Initiative is a very serious government program that tries to answer the question, will quantum computers actually work to deliver true value? It's an exceptionally rigorous evaluation. We meet with the QBI team every week. It's like having your annual exam weekly. It's just a tremendous amount of work, but we're very grateful both for being selected there as well as for the hard questions that they're asking, which I think in all make us better. Joe and Ghalbouni Consulting is part of the QuEra Quantum Alliance, and so I wanted to say a word about that. QuEra Quantum Alliance is a group of companies that partner to go to market together with neutral atoms and help customers succeed, essentially. We believe that at QuEra, we're really good at building computers, but that doesn't mean that we are equally good at all layers of the stack. And so we have people who are experts in finance, like Joe, consulting companies, delivery companies worldwide, people who are experts in quantum chemistry, companies who write compilers and middleware. And so when we go to a customer, we have the customer's success in mind, and we can bring in QuEra partners as desired, as necessary to do that. And big question, I mean, Joe, I'd love to speak to you any day of the week, but one question is, why are we doing this now? Well, I think we're doing this now because we are nearing a very interesting point in the timeline of quantum computing, because three forces are converging to being able to deliver quantum value perhaps sooner than most people thought. On one hand, the computers are getting better, more qubits, better qubits, easier to use, easier to deploy. Similarly, quantum error correction, the ability to make computers more resilient to errors, is improving dramatically. And at the same time, the algorithms are getting better, both in terms of new algorithms as well as a way to make them more efficient. So if I were to demonstrate this sort of semi-graphically, people have always said, okay, well, if computers are here and the algorithms are there, how big is the gap, right? How many years do I have to wait? So say if we talk about security, okay, RSA 2048, when can I run Shor's algorithm and break the internet on? Let's assume you wanted to do that. So on one hand, you have computers that are getting better. And on the other hand, even for Shor's algorithm, there are more and more and more efficient implementations. And so that gap is narrowing quicker than the days. And therefore, we are approaching this point that between the algorithmic progress, the quantum error correction progress, and the computer progress, the time to value is getting closer and closer. So with that, Joe, maybe I can turn it over to you, and love to hear about your background, your perspective on both the risk and the opportunity for financial services.
Thank you so much, Yuval. With that, I'll share my screen and share a small presentation I've put together. Right, let me just, right, you can all see my screen. All right. So yeah, as Yuval has very well noted, there is at the same time regarding quantum technologies this aspect of strategic risk and emerging opportunity. And why do we talk about risk and opportunity? Obviously, we talk about risk because of encryption that will be broken using quantum computers. And here I mean asymmetric encryption, which I should note also concerns any symmetric key that was generated with an asymmetric protocol. This is very important to note. And also there's the risk of missing out the quantum momentum. And the reason why it's really a problem is because unlike other aspects like AI, for example, other frameworks like AI, which people have been working on for quite some time, even before the whole Gen AI and the whole capabilities of Gen AI happened, AI is something you can easily ad hoc on what you do in terms of developing any program. While for quantum, this is completely different because you're looking at a very different angle. We're still at a time where you need to understand quantum physics to some extent. We are not really at the point where you really are abstracted away from quantum physics in understanding how can I not have to learn quantum physics to really know how to deeply program a quantum computer. So with that, I'm not saying that you need obviously to have a PhD in quantum physics to know how to program a quantum computer, but we are building the stack and the tools so that you don't have to do that. So there is that risk as well, and there is the emerging opportunity of really leveraging this technology. And here, we are really lucky, I would say extremely lucky since 2023, that by looking at how AI has been evolving and how AI has been integrated, we can now understand what's the best way for us also to integrate quantum. And let me say why before I move to the next slide. So, for example, I wrote an article today about Claude Mythos, which is Anthropic's model that allows to detect vulnerabilities, right? So in terms of cybersecurity, this is really a game changer because you now have an AI that is able to detect all the different flaws, all the different cybersecurity flaws you have in your programs running at an enterprise level. So even in the deployment of Claude Mythos, it is becoming extremely restricted. Not everyone can have access to it because there's concerns and all the regulators and policymakers are jumping on it because it's really a game changer. So think of it like quantum breaking encryption. And the reason why I'm making this analogy is because now people are saying, okay, if we have an AI that is so fast at detecting vulnerabilities, then we probably need also an AI that will be as fast in fixing them, because the humans can't keep up. The machine is so automated and so fast that if it detects vulnerabilities and you're waiting for a human to fix those, this is going to take a lot of time. And the reason why I'm making this analogy is because now with quantum being a risk, you need to leverage quantum as an opportunity to counter it. So it really comes naturally that quantum is on both fronts. So the why now, the where the risk sits, the where the value sits, and the how to act. So today what we're going to explain is this aspect of the two clocks which are running, the security migration and the competitive experimentation. We're going to explain where the risk is, what are the various regulations we have today, whether it's in Europe or North America, for the financial sector, and how they already play a role into determining what you should do for quantum. Then we're going to explain in terms of use cases, where does the value sit? Because we hear a lot of things that can be done in finance or things that cannot be done in finance. So we really want here to address the use cases that are useful, at least for the near term. Obviously, in a fault tolerant regime, we're going to have even more use cases, but now I really want to focus on where the value has been shown and what we can start doing today. And also how to act. What should you do in order to have a successful quantum journey? So the first clock is the security migration, which says that readiness can no longer wait for certainty. So what we mean by this is, in case you're wondering, I'm going to wait for quantum computers to break encryption so that I do my migration. Well, let me tell you, this is probably the worst idea, because if you need to do any sort of migration, you definitely need to do a cryptographic inventory first. You need to understand where are you vulnerable. You need to do what we call a quantum risk assessment. And based on this, you need to start proposing migration. And let me tell you, this is not something that is done lightly. This is not something that is easy to do. And most of all, this is not something that is static. And what I mean by this is not static. Today, any comparison you're going to do with how vulnerable you are is always compared to the available quantum algorithms we have today and the available quantum roadmaps we have today. So a very easy example, actually a couple of examples, one of them that Yuval brilliantly mentioned, is that Shor's algorithm is requiring less and less resources to be executed. So now we are facing something that is dynamically getting closer. It's not something that is static in time where we say, okay, this is not happening before 2040. No, apparently this is happening way before. And Google, for example, announced that 2029 might be the year where Q-Day happens. Q-Day being the year where quantum cryptography, quantum computers are able to break asymmetric cryptography, and particularly the RSA and the ECC protocol and the Diffie-Hellman. So readiness can no longer wait. All the signals have been there so that you can start migrating today. And the second is the commercial advantage. Today, if you look at the estimates of McKinsey for the market of quantum computers, it's estimated in the hundreds of billions by 2035. And you cannot say, well, I'll wait for 2035 to jump on the train, because any time you're going to wait is a time you're going to have to work on again. So let me reformulate that in a more clearly manner. If let's say you need 5 years until you're operational, if you start in 2035, you won't be operational before 2040. And the reason being that it's not a matter of spending money to gain that time, it's a matter of building expertise internally. Because at the end, what you want is not simply have 120 PhD in quantum computing people who are going to join your team. You need to have your team that is able to leverage that new technology. And this takes time. You need to take time to map your use cases. You need to take time to understand which framework you're going to use. You need to take time so that any tool you use can be taken into production, can be bounded by governance, can have its proper SLAs. And all of this need a preparation. And quantum vendors, the quantum hardware vendors, are looking for partners to actually help them do that, because the partners know their field, they know their sector. And so it's very important for partners to be part of that journey so that both the quantum hardware vendors and the people in the sector are actually able to get the value of this technology. Otherwise, we're going to have very powerful machines, but we're not really going to know how to use them. So where does quantum risk sit in financial services? So first of all, obviously, there's the cryptographic exposure. Any public key dependency across the payments, the custody, the identity, secure communications, and customer channels. And if I take an example, in Europe, we have what we call the DORA Act. So the DORA Act in Europe specifies that financial institutions are responsible for all their encryption and cybersecurity aspect, even if it relies on third party. They cannot say, okay, you know what, I'm using, let's say, AWS, I'm on the cloud, let them take care of it. No, you're responsible for everything. And so if people do not know about quantum and Q-Day happens, then by the DORA Act, they are responsible of their security. So that's why there's a very strong need to do that today. And I'm not even talking about regulations that are going to be directly tied to quantum. Today, if you take the DORA Act and you read it, there's no word quantum mentioned in it. But what it expects from people is certainly aligned with them having to be protected against quantum computers, because it's an attack that is now well known and that will happen. We also have the scenario of store now, harvest now, decrypt later, right? Where people are already stealing encrypted data. And we have no way to know how much of that encrypted data has been stolen. You can indefinitely copy information in the classical way. So this is a big problem in case your data is relevant in a few years, or if it's relevant along several years, let's say data that has been stolen from the 2000s. So it's very important to address that and to start securing your encryption today. Then there's also the third party and ecosystem exposure, which means that core platform, cloud providers, payment partners, etc., all of these which are part of that cybersecurity aspect should also be taken care of. And there's finally the governance and regulatory readiness, because this is going to happen. For financial institutions, there is that question of, am I compliant? Am I regulated? Do I fall into a governance framework that is clear? And this is really the point that make financial institutions act. And the reason why I think we should not just wait for a governance and regulation to happen, because it takes a lot of time with quantum to be ready. So if you haven't addressed this aspect, you're going to probably have a lot of trouble getting compliant quickly. And again, there are a lot of legacy systems that you need to address. There's a lot of different implications, different kind of, let's call it, entanglement between those different systems that you need to address. Now, we discussed about the risk. Let's discuss about the value. Let's discuss about where the value is emerging in finance. I've given here 3 examples, but I'm going to follow that with a table of much more tailored practical near-term use cases. But basically, it really falls in the following categories. The optimization category, with, let's say, a portfolio construction, a treasury allocation, etc., any problem that requires reducing a cost function to its minimal value. There's also machine learning. Machine learning, I would take it from both aspects. There's the aspects of doing a fully quantum machine learning aspect when you are working with quantum features. This might not be extremely relevant in the finance world, but what is relevant in the finance world, however, is a couple of very important things. First of all, looking at using quantum kernels for classical data, which we are finding to be heuristically more efficient. And the good thing is that those quantum kernels do not require extremely powerful quantum computers to run. So we can really run in a hybrid world where, whether it's with QuEra computers or other vendors, everyone has been moving to the, I want to integrate that device in an HPC center. And that, therefore, all of these classical hybrid approaches work perfectly. Another very important aspect of machine learning, which is a paper that has been published by John Preskill's team about a couple of weeks ago, is that there is now a provable exponential quantum advantage when you want to treat massive data and do machine learning. And it's extremely important because today, anything you want to do in terms of fine-tuning a large language model, let's say for the financial institution, becomes much more easier to do because of that exponential advantage that you gain. And the last point in machine learning, which is extremely interesting, is that you need less data in order to get a very good result. And why it's important? Because having clean and curated data costs a lot of money. So at the time when I was working at Point72 at the hedge fund, there was this problem with Gen AI where you needed to do fine tuning of models, right? And you needed data, and you could go to multiple data providers. The data that you would need, let's say for time series, would probably cost about $1 million. So those are extremely costly data when they are curated. The fact that you can need less data helps you save a lot of money. And also the great thing is that quantum computers consume a lot less energy than their classical counterparts. And therefore, when you need to train very heavy models, or you need to fine-tune very heavy models, you're going to consume less electricity, which is a big problem currently with generative AI. And then there's stochastic modeling, where you can get with quantum computers better distribution. And why it's important is because for Monte Carlo simulations, for everything related to the value at risk calculation, you are able to calculate the tail ends of your distribution. You're able to take a model that is much more accurate than only being focused into the center of your distribution. And that allows you to do better prediction and to model let's say, to model the risk of your exposure under more various scenarios that you are taking into consideration. So that's better if you want to protect yourself against any market problem. Now, if I look a little bit at some of the use cases that are extremely interesting, and note that all of these use cases are backed up by banks, are backed up by the financial sector. So obviously, JPMorgan Chase is one of the most notable player in the field in terms of financial institution. They have their own quantum team. So they've done a lot of work over the years, a lot of great work over the years. So one problem, for example, which is the portfolio optimization, where in that case you are selecting asset. So I'm not talking about the portfolio allocation where you are allocating a budget. I'm really talking about the selection, which is a binary type of output problem. They have come out with a paper which is called the decomposition pipeline. And why this is important? Because today, the bottleneck of using these approaches on quantum computers is that you need at least 1 qubit per asset. So let's suppose you need 1,000 asset. Well, now you quickly need 1,000 qubits, right? So that becomes something that would require a few more years along the way to solve. However, with the decomposition pipeline, the great aspect is that you only need 30 qubits. Why? Because what you are doing is actually dividing your problems into a maximum of 30 qubit problem and then recomposing them. So the great thing is that this paper, for example, has provable results on today's devices. So it's really interesting to start looking at this and implement it today. So that's why in terms of feasibility and near-term justification, this one is considered to be quite high. Then you have the amplitude estimation, which is important for option pricing and the type of stochastic modeling. So the third category that we discussed of, which was out in 2020. So today, it's something that we can already start implementing. Now, the reason I say it's moderate to high is because Monte Carlo, even with all the reduction, still needs some resources to be implemented. But we can start having today some early distributions that we can calculate. And that's interesting to start to look at, because now the roadmaps have really, if I look at the paper, it was published in 2020 or 2026. In 2020, the roadmaps were not as clear as we have them today. Now we have roadmaps that have actually gotten smaller in terms of timeline. We are not looking at the 2040 mark, but rather at the 2029, 2030. So that becomes even more interesting to look at these. And dynamic deep hedging is an example of the machine learning aspect I was talking about, where in that case, you are going to use quantum neural network in a classical machine learning framework where you're just replacing the kernel with something quantum. And the advantage is that you need less features in order to get the same result, if not better. So that's the interest in the dynamic deep hedging. For the last three, obviously algorithmic bond trading, which was the HSBC and IBM paper, For this one, I note that it's an empirical result in the sense that we do not really have, in full transparency, a full argument to understand why this worked better. So that's why there was a lot of, controversy around this paper, I would say. I'm not saying that the result is not correct. I'm not saying that the work done is wrong by any mean. That's not what I'm saying. I'm saying that this remains to be tested further. Um, there's also fraud detection with Intesa Sanpaolo, and this comes down also to using quantum kernels with enhanced pattern recognition. And why this is important? Because whenever you are doing machine learning and using quantum feature mapping, you are taking your features into a quantum space, and that allows you to uncover patterns that classical machine learning can fail to do. So that allows you, for example, to reduce the number of false positives you are detecting in fraud detection. And this can also be used for anomaly detection in time series. And the credit risk analysis, which is also something that we can consider to be moderate in terms of feasibility because it requires some iterative quantum amplitude estimation, allows us to actually allows for non-integer loss given default inputs and multiple systemic risk factors to provide the quadratic speedup for a value at risk estimation and with a lower gate depth. So with all these use cases in mind, one thing that I would strongly advise is that never take the word of the article for it, in the sense that it doesn't mean it's not scientifically feasible. It just means that I would strongly suggest that you try reproducing these results in-house. Try to play with these problems, these toy problems. Usually most of these papers have the quantum circuit available, so you can try reproducing them, try to see if they work with your data, try to challenge those papers, like try to play the devil's advocate and see how well it works. And if it works well, then you are already gaining a lot of understanding in how I can implement those in-house. Now, obviously, QuEra is a very important player in the field, and we've seen that there's a lot of momentum for neutral atoms. There's, for example, Google, as you can see, which has been working on superconducting qubits, which is now also using the neutral atom modality. So that's why I strongly suggest that neutral atoms are a very important modality, a very interesting modality also for this finance type of problem. Now, here is something that with Yuval we have been putting together, which is actually how can Ghalbouni Consulting and QuEra work together in order to provide for you what we call a readiness package. So it's divided into three phases. The first phase is the phase that Ghalbouni Consulting is for the most part responsible of, which is the decision and readiness. So in that sense, we're going to understand the exposure using what we call a quantum risk assessment, which is an in-house developed framework. Understand the cryptographic and regulatory horizon, the governance posture, and the competitive context. This is very important because we need to understand for the use cases that you have, how much would you miss if you don't do quantum, and how much would you gain if you do quantum? So with that in mind, once phase one is complete, this is where QuEra steps in with phase two, which is the QuEra anchored value mapping. And in that case, there's institution-specific use cases which are mapped to neutral atom strength, platform constraints, and return on investment scenarios. So now that we are involving a quantum hardware player in the picture, there's that player that is going to say, for this use case, my architecture can be mapped best to solve, for example, use case 1, 2, and 3. And this is what you can estimate in terms of ROI. And according to our roadmap, this is when you'll have, for these different use cases, the quantum advantage. And why I'm mentioning that is because the quantum advantage in any sector is not something that happens overnight, in the sense that you're not going from 0 to 100. You're going to get several wins along the way, several advantages along the way, depending on the use case of interest. And then there's obviously phase three, which is execution and acceleration, which is also QuEra mainly involved in it, or even though with partners like Ghalbouni Consulting or others, we can definitely assist, where there's going to be a pilot design, a hybrid workflow selection, a capability build, and the path from POC to credible operating model. because obviously Yuval mentioned how much the device on AWS bracket is online. There's obviously the question of when can we take this into production? Where can we have the 99% of uptime? These questions happen all the time with financial institutions, and this is more a QuEra discussion. So this is here an example of what the institution journey could look like, right? So an example of a work plan that can be obviously tailored, but this is an example of what a 90-day path or 180-day path could look like. So without repeating myself, this is again 3 steps, which is understanding an exposure and workflow scan, a use case fit. And the use case fit is important because use cases cannot be understood in terms of quantum computing yet as vanilla use cases, in the sense that you just download that package, you execute it on your data. There's really a use case mapping that needs to be done in order to optimize the problem for your data. And that's why I've been saying since the beginning of this webinar that if you say, I'm not going to look at quantum today, I'm going to look at it in several years, you will need to redo all that work, and you're not going to be able to buy your delay because you need to do that use case mapping. And then there's the whole execution and taking into production. So with that said, if I can give some final thoughts, these are really the suggested call to action: the exposure briefing, the value briefing, and the full readiness assessment. And with that, would be more than happy to take your questions.
Thank you very much, Joe. I think this is really an exciting time to be in quantum for the reasons that we mentioned briefly. Computers are improving, the algorithms are improving, and error correction is happening. I do want to add a couple points about both neutral atoms, and you mentioned roadmaps. And then while I do that, I would encourage the audience to submit questions, and we'd be happy to address them. So first, just so there's no mystery, this is what a neutral atom computer looks like. This particular one was taken over a year ago when we were installing our computer in Japan. One of the things that you don't see here is you don't see these golden chandeliers that are associated with cryogenic cooling. Neutral atoms operate at room temperature, which is fantastically important. It saves energy. Our computers can operate on tens of kilowatts as opposed to other approaches that use tens of megawatts to have a large-scale fault-tolerant computer. Our computers use individual atoms as qubits. Atoms are perfectly identical. That means that there's no per atom calibration. We can have we've demonstrated together with Harvard and MIT, we've demonstrated thousands of atoms in the machine. We believe that can scale to tens or hundreds of thousands of atoms, hundreds of thousands of qubits on a single machine. And the fact that we can move each atom individually and get any atom we want, any qubit we want adjacent to any other qubit, that means that we can have very efficient interactions. Just as an example, imagine that you're standing in the airport in a long security line and you want to talk with someone who's 20 people ahead of you. Well, if you're standing in line, if your connectivity is fixed like it is with a superconducting qubit, you have to try to relay that message to the person in front of you and then to the person in front of them and so on, in hoping that 20 people later, the message will arrive intact. If you're a neutral atom qubit, you just walk over and talk to that person, so we can have much more efficient algorithms and therefore much sooner results. You mentioned roadmaps and how roadmaps are coming into focus, that it's no longer 10 years away, but many fewer. And lots of vendors provide roadmaps, and sometimes say talk is cheap. Yeah, you could put anything you want on a PowerPoint slide. But we do have a little bit of a framework to help evaluate roadmaps. We look at 3 topics. One on foundational capabilities. Have you demonstrated qubits? Have you demonstrated high quality qubits? And have you demonstrated software that can measure qubits in the middle of the application and then make decisions based on that, sort of the equivalent of an if-then-else statement on classical computing. Then, because qubits are fragile and they're prone to errors, and the calculations that you're talking about, Joe, require sometimes millions of operations, you need high-quality qubits. You need something that's resilient to errors. So a really important thing to consider when looking at roadmaps is have you demonstrated what's called logical qubits, these error-corrected qubits that can allow to detect and correct errors. QuEra has definitely been the pioneer in that. Harvard-led paper in December of 23, we showed 48 logical qubits, and that sort of ushered the world, we believe, into the era of logical qubit and quantum error correction. Can you scale it? What does it mean? You mentioned, Joe, that say certain algorithms require 1 qubit per asset. And as we mentioned, these are high quality qubits. So if you have 2,000 assets, you need 2,000 high quality qubits. So you need to ask the vendor, how do you get there? Can you do 2,000 logical qubits? How many physical qubits does that require? How large will the computer be? How expensive will it be? How many megawatts, or in our case, kilowatts of power will it consume? And then can you run any program on that computer as opposed to only very specialized one? And then last, as we move into the practical world of deployment, do you have algorithms that are truly advantageous? No one does quantum just for the sake of quantum. They do quantum to solve a particular problem. Do you have experience in installing, maintaining services, and keeping these systems up to production SLAs, just like QuEra has 3.5 years of experience on AWS? And what does it take to deploy such a system? And now, QuEra is not perfect, at least not today. And so, if we're being honest, we think we've covered 7 out of these 9. And, we look forward to showing how we cover the rest in the future, maybe sometimes in the near future. So I did want to ask you, Joe, as we come closer to the end of our conversation, let's talk that 1,000 asset example.
Yeah.
And let's assume that there is no computer that has 1,000 good enough qubits right now. Then why not wait? I mean, should I, as a financial services organization, just wait a year or 2 years until that computer is ready, or maybe until JPMorgan or someone else demonstrate that that can be done, and only then I can sort of.
Yeah. Sorry, your question cut at the end after JPMorgan.
I'm sorry. Should I just wait for someone else to show how it's done, or wait for sufficiently strong computers to appear before I do that?
No, definitely not. So one example was, as you can see, the reduction of resources in quantum algorithms, and the one of the example I gave with the decomposition pipeline requiring only 30 qubits is an important example, because it shows you that when you work on these problems with people from the sector, you are able to optimize your algorithms much better from a sector point of view, from what you need, where you need to get value, but also from the technical aspect, because you need to keep in mind that whether Shor's or Grover's or the HHL algorithm, all of these were developed before we knew what these machines would look like, and before we understood how these modalities would be used, how they would actually evolve. So we didn't know all the challenges we had. We considered like we have an infinite amount of resources, right? So it's like theoretically saying, if my program needs 1,000,000 for loops, then I'm just going to run 1,000,000 for loops and not worry about the rest. While we've seen that actually compressing these algorithms, making them more efficient, requires the technical knowledge, but also requires the sector knowledge. So that's why I'm saying that not only if you start working on quantum today, you'll be able to leverage these, but you'll also at a very exciting time where you can contribute, where what you do can actually make things better. So you have the understanding of the sector, you have the opportunity to partner with people who understand the technicality of it, So build this together. Do not wait, because if you wait, you cannot expect the other half to catch up and do all the rest. And if you expect this to happen, then you might fall into problems where people are going to say, you know what, I'm paying for this, I'm going to put an IP on this, and then you're going to have to buy licenses from these people to use it. And this is something that people are not realizing. And we've had that problem with operating systems. Now we have, for example, operating systems which are open source, but as you can see, we do have also some hardware which are not supported by open source software. So what do you do in that case? Either you pay a license, and in terms of competitivity, then you take a hit. So that's why you now have that window of opportunity to collaborate and to work with people from the technical side in quantum in order to put together your finance or your pharma or your logistics expertise and be able to build something together.
Financial services has been a sector that's adopting new technologies, both because of the need and also because sometimes it has the financial resources to do so. So when quantum came along, people said, "Oh, this should really go into financial services." And one example that came is, "Oh, can you do credit card processing, transaction fraud processing quicker or better?" And I think over time, people started thinking about the problem and saying, well, it's a super high speed problem. Classical is really good at it today. And therefore, maybe this is just not a good problem for quantum computing. It's not a one size fits all. So if that's correct, how do you assess which kind of problems are good for quantum computers? Is it lots of data? Is it complex data? Is it high speed or low speed? Is it something that's important or less important to solve? How do you think about assessing the fit of a problem to a quantum computer?
That's a great question. So the way I look at it is I go back to the computing complexity theory of problems. So we have what you call non-polynomial hard or non-polynomial complete type of family of problems, which means that it's a problem that you cannot solve in polynomial time. You can verify its answer probably in polynomial time once you have it, but you cannot solve it using in a polynomial time. And understanding how I can probably take one of these problems out of the NP and put it in what we call a bounded quantum polynomial time or an exact quantum polynomial time, which is here mostly relevant for chemistry for the latter, but meaning that I can solve it in polynomial time up to a certain error using quantum approach is really the holy grail of it. So when I look at how quantum can help financial services, I think there's still a lot of work that needs to be done by the financial sector and the quantum sector together in order to understand how I can take one from this place to the other. That's one way I look at the value. Another one is, to your point, yes, I don't look at the value at using quantum for doing things in real time and very fast systems, because by nature, quantum systems and quantum computers are not done to do that. But they become very interesting as a second point when you want to tackle dimensionality. Today, if you take a look at the number of qubits, it requires today 800 qubits and above to be able to hold in a quantum register all the observable classical data. So it means that once you get past the 800 qubit mark, you already can load enough data that no classical register can do. So anytime you want to go above what can be done today in terms of dimensionality of data input, that's where quantum also brings another value. A third value is how you are going to be using all that data, treating all that data. We do have the notion of quantum parallelism that comes from superposition and entanglement and magic states and other that have no classical equivalent. So today, what I'm able to do is I'm able to use to use quantum registers that have more data than any classical register can retain. I'm able to explore that data, and I'm able to possibly, for structured problems in finance or any other sector, to take that problem potentially out of the NP class and reduce it to a class of BQP or EQP problem, which is today really a holy grail of research. And we have found some of these problems which have been really our main advertising, like Shores is a beautiful example of this. we've taken the problem of factorizing semi-prime number from NP to a problem that have become BQP. So are we able to do that for various problems in finance? Probably. Have we been looking at this enough? No. So it also gets down to the question of, for cryptography, have we done that enough? No. So today, if you tell me, well, I have this, for example, new algorithm of encryption I've been using, it's not breakable by quantum computers, I'm good. Well, you might be surprised that there might be a way that will be discovered where this algorithm of encryption is broken. And therefore, that's why the recommendation have been agility. You need to be crypto agile to be able to move from one to another. But that doesn't come without its challenges. There's latency problems, there's re-encryption problems. What about your data that has already been stolen? So with that, it's really a full package to answer this question.
A few questions from the audience.
Yeah.
Can the presentation be shared? We'll share the QuEra slides, and Joe, if you're fine, you can send me.
Totally fine. If QuEra is fine, I'm fine.
And then we'll also share the recording so people can listen to it if they haven't been here. The second question was, what makes neutral atom approach for hardware beneficial for finance use cases? Well, I think two things. One is the sort of inherent advantages of neutral atoms. Very high scalability, we can get to very large number of good qubits, efficient algorithms, and availability of machine. I mean, this is a technology that's maturing. It's not some pie in the sky technology that one day will work. It works today, and it has a clear path to scaling. The other thing that makes QuEra quantum computers suitable for financial services is the QuEra Quantum Alliance, whether it's Ghalbouni Consulting or BCG or Deloitte and other members of the alliance. We really have the global coverage and sector-specific expertise to tackle these problems. There was another question. Some other vendor, not to be mentioned right now, suggested quantum for commercial will not be viable until 2029 or later. What's QuEra's views on commercial viability? Every vendor has their timeline. I think that the future is closer than most people think. And just stay tuned. Another question was, Yuval, you mentioned that the scaling of Aquila, our quantum computer, happens at the level of atoms based on the demand of quantum computing power. In what scenario the quantum computer has to be physically scaled in size? That's actually one big advantage of our approach. Atoms are, of course, tiny. We hold them at a few microns apart. We believe we can put tens of thousands or hundreds of thousands of atoms of qubits in a single machine. So we don't expect that our large-scale fault-tolerant machine will be any larger than, say, a large dining room table. They're room size, not stadium sized. Joe, any parting pearls of wisdom? What would you like to leave our audience with today?
So first, I would like to leave the audience with some food for thought. So really think about how you want to prepare for your quantum journey, because it's happening. So it mostly comes down to your preparation. You need to look at it from both the risk aspect on your cybersecurity, the risk aspect of what do you miss out by not doing quantum, and also from the opportunity. Today, you're still at a time where you can leverage this. So it's like being in the 1950s or 1940s for classical computing, even though those are really two different modalities. I don't like to compare them, but again, I'm just comparing the timeline. Now, going from 1950 to 2020 in computing for quantum is going to be much faster than it has been for classical. So that we're clear on that front. So you still have time to get on the train, but the window is not going to be kept open for a very long time. Today, people who are going to start using quantum to use quantum computers, and people are going to say, I'm still going to wait, are really going to be left out. And a great example of this is also in AI. Everyone has been, mind blown when they've looked at GPT 3.5 and the fact that they could interact with the chatbot. But if you look at the version of GPT, it was 3.5. It means there was a GPT-1 and there was a GPT-2 and there was a GPT-3. So people who were already familiar with AI knew how to leverage it very quickly. So the same thing is going to happen with quantum.
So if I were to summarize, would it be fair to say that your competitors, not yours, Joe's, but financial services companies are already working on quantum? They're generating quantum-related IP. They are benchmarking how quantum algorithms compare with classical algorithms. They are hiring and training and preparing the people to take advantage of the quantum revolution. They're creating supplier relationships to make sure that they know who the partners are. And I think they are in a fantastic point to take advantage of quantum in the very near future. And if you're not doing that, imagine what would happen if you open the Wall Street Journal tomorrow and you hear that your biggest competitor has found a way to optimize portfolios, to reduce credit risk, or to do better hedging, or to do better currency conversion using quantum computing, and now you have to play catch up. It doesn't happen overnight. It's a process, and we encourage everyone to get started today. Joe, thank you very much for your time and your thoughtful insights, and thank you, the audience, for participating with us today. Stay tuned for additional webinars from QuEra and the QuEra Quantum Alliance members.
Thank you, Yuval, and thank you, everyone.